Hey, welcome back everyone. Today we're going to be working on the advanced graphs questions from the LeetCode roadmap. So in a previous video, we covered basic graphs, which mostly covered BFS, DFS, and some simple algorithms on grids. So now we're going to be looking at advanced graphs, which are graph questions that require other algorithms to go with them. For example, things like priority queues or adjacency lists. So let's get started on these. This video, we're going to cover the first three questions. So reconstruct itinerary, min cost, and network delay time. So first of all, reconstruct itinerary. In this question, we're going to be given a list of airline tickets, the from and to for each ticket, to represent the departure and arrival airports. So we want to reconstruct this itinerary and return it. All the tickets belong to a man who departs from JFK, so the itinerary must begin with JFK. And if there's multiple valid ones, we should return the one that has the smallest lexical order. For example, if we go to LGA first, that's smaller than LGB lexicographically, so we're going to return the JFK LGA one. And all the tickets can form at least one valid itinerary. And we must use all tickets once and only once. So let's look at some examples here. In the first one, this guy goes in a straight line. So there's only one way to output our itinerary, which is starting from JFK to MUC, LHR, SFO, and SJC. So that's what we output here. In example 2, this is a little bit more interesting. It seems like there's more than one way to go about this, but we're going to look at the smallest lexicographical order. So first we're going to go from JFK to Atlanta. Then we can go either back to JFK or to SFO. If we go to SFO, we can go back to Atlanta, then to JFK. So which one has the smaller lexicographical order? Well, we can see that going from JFK to ATL, then back to JFK is smaller because J comes earlier in the alphabet than SFO. So we're going to go from JFK to Atlanta, back to JFK to SFO, and then back to Atlanta. So that's what we're going to output here: JFK, ATL, JFK, SFO, ATL, SFO. So in this question, we're going to have to use a adjacency list to store all the from airports and all the to airports. So to do that, we can create an adjacency list. This is ADJ. This is going to be a default dictionary, and it's going to be initialized to an empty list. So now we can look at every ticket. So there's source and destination. Let's call the SRC and DES. So for source and destination in tickets, adjacency list of source, we should append the destination. So from the source, we can go to the list of destinations here, and that's recorded by the adjacency list. Now remember, this question wants us to return the smallest lexicographical itinerary. So for every source, we want to sort all the destinations, so we try the smaller lexicographical destination first. For example, we try this one that starts with an A first after the one that starts with an F. So to do that, we can do for SRC in ADJ. So for every source in adjacency list, we want to sort it. So adjacency list at src.sort. So now it's going to be in alphabetical order. And to do this question, we can try a backtracking approach because we know that not every way is going to work. So if it doesn't work, we're going to have to backtrack and go back. So we covered backtracking in a previous video before, but the basic idea is that we're going to try every approach. If it doesn't work, we're going to revert to the previous one. In this case, we're going to revert to the previous airport, then try the next destination from that airport. So to store where we're at, we can use a stack data structure. And the stack is going to be initialized to JFK because the question says we have to start from JFK. So the stack is going to be initialized to an empty list, and that's going to be storing JFK. And we should also have our result. Result is going to be just our answer, and it's going to be an empty array at the start. So like all backtracking questions, we should check that while stack is not empty. So while, let's do len stack is greater than 0. So there's still elements in the stack. The element that the airport we're currently at is going to be the last one in the stack. So let's call that airport, or we can just do a while loop. So while adjacency list stack -1. So the last element in the stack is the one that we pushed in last because stack is first in, last out. So while this is the last element still has things, or still has destinations to go to, we try to go to that destination. So stack.append, and what we're appending is the next destination. So adjacency list stack -1. So this is the source basically. And from the source, we're going to pop out the 0th index, or the airport at the beginning of the list. The airport at the beginning of the list is going to be the smallest alphabetically. So that's the one we're going to try first. And that's what pop0 does. Pop0 pops from the 0th index. And if that works, or if it doesn't work, either way, we're going to pop out this element from the stack. So res.append stack.pop. So we're going to pop that from the end of our stack. And after that, we can just return our answer, or it should be answer here. Let's try running it. Okay, it seems like our answer is in reverse order. And that makes sense because when we're popping from a stack, the first element that we actually want to go to is JFK, but that's going to be popped last, which means it's going to be at the end of ans. So what we're going to do is we're going to return the reversed version of ans, so reversed ans. Let's see if that works. Cool. Let's try submitting it. So this question is a backtracking question. Basically, we're given an itinerary of tickets and we're trying to find the order of it. So what we do in this question is we're going to try all the airports all the destinations from the starting airport, starting from the smallest alphabetically to the largest alphabetically. And if that works, then we're going to try the next one and just go further and further into our adjacency list. Or if it doesn't work, we're going to have to pop that from the stack and then start trying the new one. And because we're popping from the stack, the last element is going to come out first. So we're going to have to return our answer in the reversed order. So that's this question. Let's move on to the next one. Min cost to connect all points. So in this question, we're given an array of points representing integer coordinates of some points on a 2D plane. So we're given the x coordinate and the y coordinate. And the distance connecting 2 points is the Manhattan distance, which is the absolute value between the x's, and plus the absolute value between the y's. And in this question, they want us to return the minimum cost to make all the points connected. And all the points are connected if there's one simple path between any 2 points. So this graph is hard to see. Let's go back to light mode. Just for this question, we're going to do it in light mode because the nodes here are black. So here, we're looking for the minimum cost, which is the minimum distance between all points, so we can draw edges between them and have them be all connected. So in this question here, the answer we return is going to be the sum of the costs, which is going to be 9 plus 3 plus 4 plus 4. And in this drawing, this is the minimum one. So this question, in other words, is asking for us to find the minimum spanning tree. So a minimum spanning tree is exactly what the question says, which is the shortest distance to connect all the points. Usually, the minimum spanning tree is going to be looking at the distance between this, but now we're looking at the Manhattan distance, which is slightly different, but we can just use a simple function, def get dist, to calculate the Manhattan distance. So let's say we have 2 points, P1, P2. The Manhattan distance is going to be, we want to return the absolute value of P1, 0, that's the x coordinate, minus P2, 0, plus the absolute value between the y coordinates, which is P1, 1, minus P1, 2. Oops, it should be P1, 0, minus P2, P1, 1, minus P2, 1. So that's what we're going to be returning. So in this question, we can start with any of the points because all the points have to eventually be connected. So let's say we start with the point at index 0. So let's say start is going to be the point at 0. To find the closest, so we're going to do an algorithm where we're looking at the next point we want to connect. So there's a bunch of different points we can connect from the 0th point. Connected this one here, the top one, this one here, and the one on the right. So which one are we going to connect to? We can look, we want to find the minimum distance, so we can see to connect the closer point. So if we connect this point at 0 and this point at 2, 2, then these two are going to form one connected component. Then we can find the connection between this connected component to all the other points. So once we find the next closest point, for example, the one at 5, 2, then these three here is going to form one connected component, and we're going to find the closest distance from this component to the next point. For example, the one at 7, 0, it's going to be closer because it's going to be close to 5, 2. And finally, this point at 3, 10, it's going to be close to the point at 2, 2, and all these points form a single connected component. So what the algorithm I described here was called is Prim's algorithm. So basically, we're trying to start from any of the points, find the closest one. Those two are now one component. Then from this component, we find the closest point to the component, which is going to be this one. And then we repeat until all points are connected. So to do this, we need to keep track of the minimum distance from our starting point or from our component to all the remaining points. So let's say our start is 0. So the minimum distance at the start of the question, it's going to be the distance of 0, and then the point index is going to be 0 as well. So this is going to be a min heap, and what the min heap stores is going to be the distance and the index of a point. So we should also keep track of which points we've already visited, because we don't need to add those points to our component anymore. So visited is going to be equal to a set. So now while the length of visited is less than the length of points, so while not all points are visited, in other words, not all points are connected, we're going to have to find the closest point. So to find the closest point, we're going to pop from the minimum distance, which gets distance and index. So let's just call that ind. This is going to be from heap q, heap pop, and what we're popping is from the min distance. This is our min heap here. And our new point is going to be the point at index, ind. So equals to point ind. So now we want to check if this new point has actually been visited already, because in that case, we don't want to visit it again. So if ind visited, we can just continue and then pop again from the min distance. So if it's not visited, then we should add it to visited so we don't visit it again. So visited.add index, and answer should plus equals to our distance. Because our answer is the total distance, so whenever we add a new point, we should be adding that distance to our total distance. So now from this new point could be closer to the remaining points than our component previously was. So from that new point, we should check the distance to all the unvisited points. And if that's closer, well, we should be pushing it into our min distance. So we can check that later. So now for I point and enumerate points. So looking at all the points, if the point is not visited, that's the points we care about. So if I not in visited, heap q dot heap push, we push onto the min heap, so min distance, and the distance we're pushing is get dist from our new point all the way to the point. So point is the neighbor of new point, and we're going to get all the distances, and then we should also record the index I, and these should be in a bracket because they're one tuple. So now we push this combination of distance and index onto our min distance in case that gets updated. So now when this for loop ends, that means we visited every single node in this graph, in which case we should just return answer, because whenever we visit something, we're adding the distance to our answer. So we're going to return answer. Let's try running that. min dist is not, it's min dist. Made a typo there. Let's try running it again. And this should be points. Forgot to initialize answer, so answer should equal to 0 at the start. And we don't need the start variable. So let's get rid of that. Let's try running it. Cool, that's accepted. So let's submit it. Nice. So let's go back to dark mode first. So this question is Prim's algorithm. Like I've said before, whenever we have a point, we're going to find the closest point to it, form a component, and then find the next closest point to join to our component until every single point is connected. There's also another algorithm called Reconstruct algorithm to find the minimum spanning tree. That works too, but it's a little bit more complicated because we need to code up union find, which I've done in a previous question, but we're not going to do that for this question. So Reconstruct's algorithm, unlike Prim's, is going to look for the minimum edge as opposed to the minimum point. The minimum edge is the edge with the least distance, and we're going to add it to our answer if that edge does not form a cycle, because the minimum spanning tree is a tree. We don't want any cycles in it. So we're going to add the closest edge, or the edge with the shortest distance, to our connected component if and only if it doesn't form a cycle. So that's Reconstruct's algorithm. We're not going to code it here. So let's move on to the next question. So next question is network delay time. We're given a network of n different nodes labeled from 1 to n. We're also given times a list of travel times as directed edges. So u, v, w, u is the source, v is the target, and w is the time it takes for the signal to travel from the source to the target. And we're given a source node k. So k is the node that sends the signal, and we want to find the minimum time it takes for all n nodes to receive the signal from k. Or if it's impossible for them to receive the signal, then we want to return -1. So let's look at the examples here. In example 1, k is 2, so 2 is the source of the signal. Now 2 has to send the signal to every other node. So it takes one time to send to node 1, takes 1 time to send to node 3, and it takes 1 time for 3 to send to 4. So in total, we're going to have to take 2 times because it takes 1 to go to 3, then it takes another to go to 4. So after 2 timestamps, we're going to have reached every single node. So this question, pretty similar to the previous question. It's not Prim's algorithm, but we're looking for the shortest distance as opposed to the total distance from a source node to all the other ones. So to code this, we should also be looking at the minimum distance because we also always want to take the minimum path. For example, if there's a path from 2 to 4 that takes significantly longer, we should be doing the minimum path to 3, then from the 3, the minimum path to 4. So first of all, we should create an adjacency list because in this case, not all nodes are connected, only the ones in times are. So we need to record which ones are connected. So let's create an adjacency list for a default dictionary initialized to a list. Now for u, v, w, the question says u is the source node in times. So u is a source node, so adjacency list from the source dot append to the target. Let's create a tuple, the target, and the wait time. So v and w. Now we should also create a set for visited. So visited equals to a set. And we should create a min heap because we always want the minimum time it takes from k or from any node to the next one. So min heap equals to, it's going to record the distance and then the index. So the distance at the start is going to be 0 because we're starting off at k, and the index is going to be what k is. So now our answer is going to be 0. And our answer is always going to be updated for the longest distance from k to any target node. So now while len visited is less than n, so while we haven't visited every single node yet, we're going to try to visit them. So first we should check if there are no more nodes in our min heap, because it's possible that it's possible that it's impossible for all n nodes in this question, in which case we want to return -1. So we should check that if there's no more things in min heap, we want to return -1 because we haven't reached all n visited and we've already run out of options, in which case we want to return -1. So now we're going to be popping from our heap. So what we pop out is going to be the distance as well as the index. So what that pops out is heap q.heap pop, and it's from our min heap. So the distance is going to be the distance from k to the node, and the index is going to be the index of the node. So now again, we should check if index is already visited. If it's already visited, we don't want to visit it again. So if ind in visited, let's just continue and pop the next one. So suppose it's not visited, we should definitely add it to visited. So visited.add our index, and we should also update our answer, because to visit this node, we take a time of distance. So if distance is greater than our answer, then that is going to be the longest time we have to wait. So ans equals to max dist and ans. So now for every node, or every neighbor in the node that we're currently visiting with index ind, we're going to look at its neighbors and see if we can pass the signal on to them. So now for v and w in adjacency list of ind, let's look at our neighbors and then push that. So heap q.heap push, what we're pushing is into the min heap, and we're pushing the distance that it took to travel from k to our current node as well as w. So the distance it takes to travel to the next one is going to be the distance it takes to travel to the current one plus w, which is the time it takes from the current one to the next one. So the total time is going to be distance plus w, and we're also pushing the v, which is the index of the next node. So now once every single node is visited, or len visited equals to n, or we return -1, in which case we already returned. So if we haven't returned, then we're going to be returning answer. And answer is going to be the answer after visiting every single node and seeing which distance is the greatest. So let's try running this. Cool, that's accepted, and let's submit it. Nice. So this question is a slightly modified version of Dijkstra's algorithm, where we're looking for the shortest distance to go from a source to a target. Dijkstra's is only looking for one target, but here in this question, we're looking for all the targets, and we're trying to find the maximum time it takes to reach any of the targets. So that's it for this question, and that's it for the video. We're going to be continuing the rest of the roadmap for advanced graphs in the next video. So thank you guys for watching. Hope you learned something, and I'll see you in the next video.